4 billion years ago, a chunk of dirty ice a few kilometers wide slamming into Earth could decide whether future oceans formed or whether the surface stayed dry and lifeless rock. To understand why, we have to rewind to the early solar system when our planet was still forming and far more violent than it is today. Back then, space wasn't empty, it was crowded. Leftover building blocks of planets, asteroids and comets were orbiting in chaotic intersecting paths. Gravity kept stirring this cosmic gravel, and some of it was inevitably thrown inward, toward the young Earth. This era, especially a period around 4.1 to 3.8 billion years ago, called the Late Heavy Bombardment, saw impact rates thousands of times higher than today. Each impact was not just an explosion, it was a delivery of rock, of metal, of ice, and possibly of the ingredients for life. Comets are particularly interesting because they are cold storage units from the solar system's childhood. Their nuclei, the solid cores, are mixtures of water ice, frozen gases like carbon dioxide and carbon monoxide, silicate dust, and complex carbon-rich molecules. When missions like ESA's Rosetta visited Comet 67P, Churyumov-Gerasimenko, its instruments detected amino acid-like molecules, simple sugars, and a zoo of organic compounds. These aren't living things, but they are the chemical alphabet from which biology can write more complicated sentences. If such a comet hits a young planet, it doesn't just bring water, it delivers chemistry. But did comets actually bring Earth's water? Measuring that is surprisingly subtle. One clue is hidden in the hydrogen atoms inside water. Hydrogen comes in different isotopes: ordinary hydrogen with one proton, and deuterium with a proton and a neutron. The ratio of deuterium to hydrogen, the DH ratio, in Earth's oceans is about 1.5 parts per 10,000. When we measure the DH ratio in many comets, using spectroscopy and spacecraft, it often doesn't match. Many comets from the Oort cloud have roughly twice Earth's value. That suggests that those comets cannot be the primary source of our oceans. Some Jupiter family comets, which likely formed closer in, have DH ratios closer to Earth's, so they might have contributed. But current evidence points to a large fraction of Earth's water coming from water-rich asteroids, not comets alone. So, if comets might not have filled the oceans, why do they still matter for the origin of life? Because organic molecules are harder to make than water. In the cold outer solar system and in interstellar clouds, radiation and cosmic rays slowly assemble complex organics on the surfaces of icy grains. Comets lock this chemistry in place for billions of years. When they impact a planet, some of this fragile cargo is destroyed by intense heat and shock, but not all of it. Laboratory impact experiments and computer simulations show that pockets of material, especially near the back of the impactor, can survive or be only partially altered. The result is a rain of organics into the atmosphere, the oceans, and even into sheltered environments like pores in rocks or deep-sea hydrothermal systems. In those early environments, warm little ponds, mineral-rich shorelines, high-pressure vents on the ocean floor, comet-delivered compounds would have mixed with molecules produced locally by lightning, ultraviolet light, and volcanic activity. Minerals could act like catalysts and scaffolds, concentrating and organizing these molecules, encouraging them to form longer chains like RNA precursors or membrane-like structures. We don't yet know exactly where or how life first sparked, but comets expand the chemical budget, making it more plausible that, somewhere, a self-sustaining network of reactions crossed the line into biology. They don't solve the origin of life by themselves, they tilt the odds. Even today, every time a comet grazes past the sun, we're watching a fragment of that ancient delivery system in action. A reminder that planets and life are not isolated projects, but collaborative efforts of an entire planetary system. And once you see comets as potential seed bearers, a larger question emerges. If they can enrich one young world, what might they be doing to all the others?